Lecture 16 covers sections 5.7 through 5.8. At the end of today's lecture, you should be able to find the absolute temperature scale in general and for ideal gases. For us to begin, we have to talk about our absolute temperature scale. Now recall the 0th law of thermodynamics to establish the equality of temperature. We can define an absolute temperature scale that is independent of any property of matter. That is, when we said two bodies were in thermal equilibrium with a third body, they had equality of temperature. And if we had a temperature scale, it'd be very easy for us to say whether or not bodies were in thermal equilibrium. The thermodynamic temperature scale, also known as our absolute temperature scale, is the absolute measure of temperature in SI units, and is defined by the second and third laws of thermodynamics. The third law of thermodynamics states the entropy of a perfect crystal is zero at absolute zero. That is, at absolute zero, a material is going to be at its minimum energy. Now, when we speak of temperature of a system, we're going to imply it's in thermal equilibrium. When we analyze a Carnot cycle, our heat engine provides thermal communication between our high temperature and low temperature reservoirs. That is, our heat engine directs a quantity of heat, QH, from our high temperature reservoir into the heat engine, and it rejects QL to our low temperature reservoir. The second proposition of the Carnot cycle states that two reversible heat engines operating between the same temperature reservoirs, TH and TL, must have the same efficiency. And recall the efficiency of a Carnot heat engine is our power output per heat input, QH minus QL per QH, or 1 minus the quantity QL per QH. That is, the efficiency is going to be a function of temperature, since our heat engine is operating between a high and low temperature reservoir. That is, we can say the efficiency of our Carnot cycle is equal to 1 minus psi, which is a function of TL and TH, where psi is a functional relation operator. Let us imagine that we have a reversible heat engine operating between a high temperature reservoir T1 and a low temperature reservoir T3. We can see Q1 enters our heat engine and Q3 is rejected. Now, let's interject an intermediate temperature reservoir that has a value T2, where T2 is less than T1 but greater than T3. And we place two reversible heat engines between T2 and T1 and T3. That is, HE2 is going to exist between T1 and T2, and HE3 is going to exist between T2 and T3. We see Q1 enters HE2, and it rejects Q2. Q2 then enters HE3, which rejects Q3. The efficiency of our first heat engine, HE1, that exists between T1 and T3, will be the same as our system of two heat engines existing between T1 and T2 and T2 and T3. That is, the efficiency of our first heat engine, eta HE1, would be Q1 minus Q3, which is the work of our first heat engine, per Q1. The work of our second heat engine is Q1 less Q2. The work of our third heat engine is Q2 less Q3. The work of those two heat engines combined is Q1 less Q3. Therefore, the efficiency of those two heat engines is Q1 less Q3 per Q1, which is the same as our first heat engine. The efficiency of our first heat engine is existing between T1 and T3. So we're going to say eta HE1 will be equal to unity minus the quantity Q3 per Q1. Or Q3 per Q1 is going to be equal to our functional relation operator psi that's going to be a function of T1 and T3. T1 and T3 serve as the inputs that allow us to determine a value for Q3 per Q1. The efficiency of our second set of heat engines uses Q2. That is, the efficiency of our heat engine 2 plus 3 would be Q1 less Q2 plus Q2 minus Q3, which was our net work from the two heat engines per Q1. Or we could express this as 1 minus Q2 per Q1 plus the quantity 1 minus Q3 per Q2 times Q2 per Q1. We can express this in terms of our functional relation operator. That is, within our first parenthesis, 1 minus Q2 per Q1 will be psi as a function of T1 and T2. In our second term, 1 minus Q3 per Q2 times the quantity Q2 per Q1 yields a function relational operator that is a function of T2 and T3. We will not include T1 since that's already taken care of for our first quantity. Since the efficiency of our heat engines are equal, the functional relation operators must be equal. That is, psi as a function of t1 and t3 has to be equal to psi as a function of t2 and t3 times psi as a function of t1 and t2. We notice that the left-hand side of our equation is not a function of t2, although our right-hand side is. Therefore, the products of the two terms on our right-hand side must eliminate t2. And this is only achieved by using a monotonic function g. We're going to call g of t just being equal to t. We'll define psi of t2 and t3 as gt3 per gt2, and psi of t1 and t2 as gt2 per gt1, and psi of t1 and t3 as gt3 per gt1. We see that when we multiply psi of t2 and t3 with that of psi of t1 and t2, our t2 terms cancel. That is, on our right-hand side, if we take psi of t2 and t3 times psi of t1 and t2, and using our monotonic function, we'd have g of t3 per g of t2 times g of t2 per g of t1, which would yield g of t3 per g of t1. And this would be equal to our left-hand side, where we'd have g of t3 per g of t1. Therefore, if we express psi in terms of our monotonic function g of t, and we choose our reference temperature, we can have a temperature scale. That is, g of t3 is equal to t3, as by definition of our monotonic function. And g of t1 would be equal to t1. And this quantity we said would be equal to q3 per q1. Therefore, the efficiency of our Carnot cycle can be expressed in terms of our temperature scale. The efficiency of our Carnot cycle, 1 minus QL per QH, can now be represented as 1 minus TL per TH.